Hey guys, today we're going to look at properties of definite integrals and ways that you can evaluate definite integrals if you are given certain information to start off with. Excuse me. The first thing that we might actually want to do is to draw a graph to kind of represent a visual. And so I'm going to, down here, just in the bottom right hand corner, oh, we're going to sketch a graph starting with A, B, we'll stick a C in the middle there, and then I'm just going to draw some function so we can kind of talk about the area under that curve involving these bounds. Okay, so we're going to start with our first one. So our first property of definite integrals that you have to know is that if you take the integral of f of x dx, usually we take the integral from a to b, so from some lower bound to some upper bound, but you can see that these are flipped. And that's would be if you were taking the integral from your upper number to your lower number. So instead of considering in the visual, instead of considering the area from a to b, going this way, right? I'm finding all the area of your infinite rectangles of your Riemann sum from A all the way up to B. I'm flipping it and going this way. The only thing that does is that area itself, the numerical value would be the same, but it would end up being negative if you took the area backwards, quote unquote. So to evaluate this integral, you would just have the opposite sign of the normal area. Next, we have my second favorite calculus insult that I like to say. So if you're taking the integral of f of x dx from a to a, if we look on our graph that we drew down here, and if we're considering the area under your curve, but your bounds don't change at all, you're finding the area from a to a, the width of that rectangle would be 0, so the area of that rectangle would be 0, which means that the integral, if you have the same bounds, the integral is 0. So I like to say you could insult somebody by saying they have the integral from a to a of f of x dx friends, and sound like a giant nerd. So there you go. If you have the integral of a constant from a to b, and we consider, I guess I probably shouldn't use c quite down here yet. If we have the integral of a constant from a to b, so some constant function, then your area under that curve is just the area of the rectangle. So it would be the constant itself, so the height times the width, which would be b minus a. And so if you have the integral of just a constant function, you can calculate that by doing the constant itself times the width of that rectangle, b minus a. Down here, if you have the integral of a constant times f of x dx from a to b, in this one, this is just kind of a property that it's not easily shown on the graph, but what you can do is you can pull that constant out front and then just find the area under the curve and multiply it by that constant itself. If you found the integral of two functions being added together, you can find their areas separately and then add those areas together. So there you go. Same thing with subtraction. All right, and then down here, this is where I needed that C from previously, so we're going to change how we're using a C. So now pretend that there's some C value in here. And basically this is, I like to think of this as kind of the transitive property of definite integrals. So if you have some integral from a to c, so you're finding the area under your curve from a to c, so this area right here, and then you add that to the area from C to B, this area right here, what that actually gets you is the total area from A to B. And so what it does, I like to think of it as when you're adding the pieces together, you kind of cancel out the fact that you had to take the integral to c. So you can kind of think of it as, and don't actually do this, but you can kind of think of it as removing those and then just taking the integral from your very lowest limit to your very upper limit. All right. And then last but not least, we're going to hit this more in our next unit, applications of derivatives, but I thought it might be wise to present it here. This is the integral from a to b of f of x dx, and so basically this is saying if I take the total area under my curve, so I don't have a c value anymore. So if I take this total area under my curve, which is just this piece of it, and then I divide it by the distance from B to A, basically what you would be finding is you would be finding the average area under your curve, or the average value of your function. And so whenever you see this formula or whatever you're asked for the average value of f of x, that this formula should come to mind. It is different from average rate of change, and like I said, we'll get into that in more detail in our next unit. But again, just wanted to introduce it here. And so if you're asked to find the average value of a function, this is the formula you'll use. Or if you're asked to interpret an interpret an integral, you could say that this is the average value of whatever that function is in there. So the average value, or the average velocity, the average number of bananas, the average rate at which the moon is traveling. It all depends on what your function is in here, okay? So those are your properties of definite integrals, and so now you can go ahead and do a little bit of practice on those. Thanks, guys.